thank you very much to the chairwoman and to all of you for being here. And over the next 25 minutes, I'm going to try to introduce you the world of electrochemistry and how electrochemistry can help you in your research work. And to do this, I'm going to follow, well, okay, it doesn't work. So, is like this? No. No. Okay, now it works. I'm going to follow these contents, okay? And in these contents, you can see that first I'm going to introduce what is the relation between environmental and electrochemical engineering. Then I'm going to focus on the application of electrochemical technology in water and wastewater treatment, because we are in a school about advanced oxidation processes. And then I'm going to focus on the two key processes for you, that are electrolysis, anodic oxidation, and enhanced mediated electrolysis. Then some remarks, and finally I'm going to show you how to design an electrochemical treatment for water treatment. I don't know if we are going to have time in 25 minutes. If not, you have this material to do homework, okay? Perfect. So my first question, no, my God. My first question is, perhaps you are thinking that I'm going to try to convince you that electrochemical technology is very beautiful, it's nice, and that you can use it every time, okay? This is not what I met here, okay? I met here only to show you in which things electrochemistry can help you. And in that point, I have a question for all of you. Do you have an electrochemical reactor next to you? Who has an electrochemical reactor? Only 2 people. So show me your mobiles. In all the mobiles, you have a battery. And the battery is an electrochemical reactor. So this means that electrochemistry is very close to you. Okay? It's not only this application. Okay, the chlor-alkali industry produce 2 of the most important commodities. You have the production of metals like aluminum. You have the desalination of brackish water by electrodialysis. You have a production of adiponitrile by means of the Monsanto process. You have many electrochemical processes. And perhaps you have to ask you, can electrochemistry be used in environmental engineering? And then you have to focus in water, in gaseous streams, or in soil. But let's focus in water. In water, you have 4 types of facilities. My God. I have a big problem with this pointer. Industrial wastewater treatment facilities, wastewater reclaiming facilities, urban wastewater treatment facilities, and water treatment facilities. And among them, my God, perhaps you think that the best application of electrochemical technology will be in the treatment of industrial wastewater, in which you can use electrolysis for the treatment of organic and metals. You can use electrodialysis for the desalination and purification of streams. And you can use electrocoagulation for the treatment, for the removal of colloids, or for the breakup of emulsions. You can also use electrochemistry in water treatment facilities. You can remove organic matter by electrocoagulation. You can desalinate by electrodialysis. And you can disinfect using electrolysis. You can also treat gaseous by using combined adsorbers, electrolyzers. And you can also treat soils. This means that you have plethora of possibilities of using electrochemical technology in environment technology. Well, and what are the advantages of our technology? The first advantage is that our reagent is the electron. Can you see electrons? No. So this means that you cannot pollute with electrons. So we are using a very clean technology. And we have a versatile technology. We are using many processes at a time. We can produce chemicals where we want and in the amount that we want. We can treat volumes from milliliters to cubic meters. And our processes can work at room pressure and temperature. We can have a good selectivity. Our processes, we are going to tell you later, can be operated very easily, can be automated very easily, and sometimes they are cost effective. So, initially, they are very promising. First point important in the lecture. What is an electrochemical reactor? It's an heterogeneous reactor. And this heterogeneous reactor has two important points. The electrodes, one anode and one cathode. In the anode, we have oxidation processes. And in the cathode, we have reduction processes. And in the electrolyte, we have the transport of anions and cations. Anions from the cathode to the anode. Cations from the from the anode to the cathode. And we can place in this reactor here, we can place a membrane. So we can prepare different compartments inside our reactor. That it is something that we can use very efficiently. Second point, what are the main parameters that we need to study electrochemical processes? Well, for me, one of the most important parameters is the current intensity, because the current intensity is related to the reaction rate. By fixing the intensity, the current intensity, I fix the reaction rate of an electrochemical process. And this is very important, okay? I also can fix, in the case of a cell in which I separate ions, I can fix also the transport of ions through this membrane. So this is one of the key parameters that I'm interested in. Second, cell voltage. If I have to teach something on fuel cells, for me is a friend. If I'm teaching here, for me the cell voltage is an enemy. And it's an enemy because I have the higher the cell voltage, the higher the price I have to pay for an electrochemical process. And this cell voltage is the sum of many factors, okay? Some factors are needed, okay? You need the minimum cell voltage to produce the electrochemical reaction. But other factors are ohmic losses and are only related to the production of heat in our reactor. So we are paying to produce heat, and this is not good, okay? So we are wasting money. More points. For me, it's not important time, okay, in an electrochemical reactor, because I can do something in 5 minutes or in 1 hour. The key point here is the specific applied current charge. I mean, the amperes per hour amperes hour per cubic meter that I'm using, okay? And this specific applied current charge is related to the specific power consumption by multiplying this value by the cell voltage. This means that I can easily calculate the power consumption of an electrochemical processes by using this equation. More points. What are the key technologies in water treatment, the key electrochemical technologies? Basically, 3. Electrocoagulation. Electrocoagulation is the same that chemical coagulation. And the difference is that instead of using a salt, of adding a salt, what we are doing is to dissolve an electrode, an aluminum of an iron electrode. And that inside the electrochemical cell, by the reaction of oxidation of water or the reaction of reduction of water, we are producing bubbles. And these bubbles can help to separate the flux that are formed inside the electrocoagulation cell. Second important technology, electrodialysis, is not a reactive but a separation unit. And in this separation unit, what we are placing is different configuration of membranes, and that help us to concentrate and dilute salts. And that we can use this technology for purifying streams, or we can use this technology to concentrate salts, okay, or to dilute water, okay? And the third technology that is the most related with this school is the electrolysis. And electrolysis means that we are going to change the chemical composition of wastewater by using electricity. Okay? And we can change the chemical composition in many ways. We are not only going to oxidize organics. We can oxidize inorganic compounds. We can produce chemicals, chemical oxidants. We can dehalogenate halogenated compounds. We can reduce inorganic pollutants. We can electrodeposit metal ions on the surface of a cathode. So by electrolysis, we can do many, many different things related with environment, with the improvement of the quality of water. Okay, and then I continue to the following point. And the following point, I'm going to focus in one application that it is related with this AOP school, the electrolysis, the anodic oxidation. What does this mean? Trying to oxidize wastewater directly on the surface of an anode. Okay, and this process is a complex process that depends on many factors, mainly on two. First, the electrode that I'm going to use. Second, the cell that I'm going to use. Regarding the electrodes, I need electrodes with very good properties. Okay, but I have to choose the electrodes for a given application. In this case, I want to look for anodes that are good for the oxidation of organic matter. And I need cathodes that can be good for other things that I can do inside water. What happens really in the nearness of the anode is not a simple process. There are many processes happening at a time. The pollutants has to arrive next to the anode surface, and then they can be directly oxidized to product that they have to move to the bulk of the solution. In addition, we can produce on the anode oxidants, and these oxidants can attack the organic matter next to the anode, or they can attack the organic matter in the bulk. And we can activate these oxidants using different technologies, such as light irradiation, such as ultrasound application, or such as chemical activation. Okay? So if we are clever, we can have very efficient processes by combining technologies inside our electrochemical cell. What about the types of anodes? You can see in the books many different classifications of anodes. I'm going to classify them into two categories: lowly efficient anodes and highly efficient anodes. Okay? Anodes that I like the MMO, okay, mixed metal oxide, or iridium oxide, or ruthenium oxide anodes that are lowly efficient. And what does this mean? This means that we produce oxidation of organics, a very soft oxidation of organics, okay, with the production of many intermediates, with low production of carbon dioxide with a slow oxidation rate and small current efficiencies. And that I don't recommend to use this in these applications, okay? And you can have highly efficient anodes, like the conductive diamond anodes or the lead dioxide anode that produce almost directly the mineralization of the organic compounds contained in wastewater, okay? And that are very efficient. In fact, this graph is very beautiful because it shows you that if you have a very high COD and you treat wastewater with a very high COD, every electron that you pay is an electron that you are going to use to oxidize, okay? You can have a 100% efficiency by working from a very high value down to more or less 1,500 ppm of COD, okay? And from this value down, what you have is a linear decrease in the efficiency of the process, okay? This is a typical value for a typical electrochemical cell, commercial cell. What about the cathode? Okay, it seems less interesting because we are focusing on oxidation processes, but in the cathode, we can have many reactions. And among them, one very important is the production of hydrogen peroxide, okay, because this can lead to other processes that we are going to speak later on, and that are the electrophoton processes. As cathode, the material is not as important. It depends on the real application that we are looking for, okay? But you can use from glassy carbon to graphite or to many types of metals. And the main problem regarding the cathode is that we have to try to avoid the formation of carbonate deposits, because on the cathode you have always the reduction of water. And the reduction of water leads to the formation of hydrogen and also hydroxyl ions. And this can transform the bicarbonates contained in water into carbonates that form a deposit. And this can generate problems in electrolytic processes, okay? Well, this is about the electrodes. What about the electrochemical cell? This is very beautiful because you can have many types of different reactors in electrochemical technology. And you can combine not only the electrode position, but many factors that can make your reactor be much more efficient than the reactor of your neighbor, okay? So here, what is a typical electrochemical cell? Something like I'm showing you in this slide. A reactor that works in this range of cell voltage between 3 and 6, with in the range of current densities between 500 and 2,000 amperes per square meter, and that operates at room temperature and pressure. This is the basics, okay? But you can do what you want. And commercially, you can find from divided cells in which you can separate what happens in the anode and in the cathode by a membrane, to tank cells, okay? That is simply a tank in which you place your electrodes. Or you can use your electrodes to make compartments in the cell. Or you can use cross-flow electrodes. Or you can use many different types of possibilities, from single flow cells, filter flow cells, or special design of cells. Any kind of cell has a different efficiency, and it is very interesting to study not only the effect of the electrode, but also the effect of the cell that you are using. Next point, how to improve the anodic oxidation. We can improve by means on the enhanced mediated electrolysis. And what does this mean? This means that I want to make use of the oxidants that are produced on the surface of the electrodes in the bulk of the solution, okay? And I want that these oxidants can oxidize in the bulk anything. If I have to be oxidized on this surface, I have to transport it to this surface. So the rate of the oxidation is going to be limited by the transport rate of me to the surface, okay? But in this case, with the mediated enhanced processes, the rate of the processes are not limited by mass transfer. And how can I do this? Okay, what I need is to produce many oxidants inside the reactor. And I can produce oxidants on the anode surface and also on the cathode surface, because I can, 5 minutes only, okay, because I can feed to the cathode oxygen. And oxygen is in a higher oxidation state than hydrogen peroxide. So the generation of hydrogen peroxide on the cathode is a reduction process, okay? So with the same electron, I can produce an oxidant in the anode and hydrogen peroxide in the cathode. So I can have double efficiency in this electrochemical cell. Okay, how can I use these oxidants? I can produce the oxidants in situ in the reactor that I'm working in, or I can produce the oxidants ex situ and add to my the electrochemical reactor. In any case, I have to be very careful when I produce an oxidant, and the oxidant that I produce should not be very harmful, okay? Because otherwise, I'm not doing well. And what are the oxidants that I can produce? Anything that you can imagine, okay? You can produce the pair silver 1, silver 2. You can produce the pair cobalt 2, cobalt 3. Or you can produce chlorine, or you can produce hydrogen peroxide. Okay? Also persulfates, also percarbonates, perphosphates, anything you need. Okay? And one very important oxidant is the hydrogen peroxide that you can produce by reducing oxygen on the cathode. And that you can combine this reduction with a reduction of iron 3 to iron 2, producing in situ the Fenton reagent. This is a very efficient process. Rapidly, because I think I'm lacking time. What about the scale-up? Cesar, in the previous lecture, asked about it. Can we scale up the system? Yes. There is no problem, okay? But we have to see if we need to scale it because in our case, this technology is competitive. And what is the typical configuration of an electrochemical cell? I need the electrochemical cell, and I need an auxiliary tank because I need volume. Okay, and remember that the electrolysis cell is a surface reactor. Let me tell you, there are many commercial cells in the market, but there are many details that you have to pay attention. I'm only going to tell you some details about the mechanical design of the inlet and outlet, the flow distributor, the current feeders, about what it is a uniform current distribution or a non-uniform current distribution. In this case, you can have a very high efficiency. In this case, efficiency using the same units is very bad. When you want to make a big electrochemical cell, you don't make a very big electrode. What you do is to stack many electrolysis cells into a stack, like the one you are seeing here or the one that you are seeing there. You have to pay attention also to filters, to pumps, to recirculation tanks, to the SCADA control system, to the power supply. You have to pay attention to the measuring devices, to many things when you are going to apply this in the real scale. And also to the specific cell design, showing you that in a simple cell, okay, this is a stack made with different number of electrochemical cells, you can have very different results depending on the number of cells stacked. What additional things? We have tested this technology in real applications, in many real applications. And the technology is feasible to be applied. But not only electrochemistry. We have first to try to decrease the pollution of the water by using conventional physicochemical or biological. And then to refine the quality of the water by using electrolytic cells. These are results that we made for a group of companies regarding the wooden door manufacturing process. And in this case, you look that you have water with a quality of around between 10,000 and 15,000 ppm of COD. After the chemical coagulation, you can decrease the COD down to 8,000. After the biological treatment, you can decrease the COD down to 4,000 ppm. And with the electrochemical cell, you can decrease the COD down to the value you want. Okay? And using not very high amounts of energy. We have tested, I'm going to stop very rapidly. 25, okay. Well, we have applied this technology to many other things. Well, in conclusion, okay, I'm going to finish here. So you have to do your homework with my problems, okay? The technology works. It has to be promoted. And I think it's not expensive. The efficiency is not low, but we have to look for the right application of this technology, okay? This material is going to be given to Antonio and will be for your use. Here you have also some conclusion written and some literature that you can find useful, and two problems, okay, with design. Okay, I was thinking that you were going to stay with me for 3-4 hours. Only 25 minutes is not so much. But we have now 5 minutes for questions. Okay, perfect. So we have time now for questions. So thank you very much.